Hi everyone, my name is Dr. Chunchu Rambabu, Department of Electronics and Communication Engineering from Dr. MGR Educational and Research Institute. Today I am going to present the topic Introduction to Control System. What is a system? When a number of elements or components are connected in a sequence to perform a specific function or operation is called a system. In a system, when the output quantity is controlled by varying the input quantity, then the system is called control system. Generally in control system, the output quantity is called controlled variable or response. The input quantity is called command signal or excitation. Examples for control system: controlling pressure, temperature, light, fan, motor, etc. Control system is divided into two categories. One is open loop system, second one is closed loop system. What is open loop system? Any physical system which doesn't automatically correct the variation in its output is called open loop system. We can define in some other manner, like the output quantity has no effect upon the input quantity is called open loop system, which means the that the output is not feedback to the input for correction. In open loop system, the output can be varied by varying the input. Examples: electric hand dryer, automatic washing machine, bread toaster, automatic tea coffee maker, light, switch, remotes, etc. These are the examples. This is a diagram for open loop system. This is called the system input and output. There is no feedback here. Next, closed loop system. Closed loop system in which the output has an effect upon the input quantity in such a manner as to maintain the desired output value are called closed loop system. The open loop system can be modified as a closed loop system by providing a feedback. The provision of feedback which automatically corrects the changes in output due to disturbances. Hence, closed loop system is also called automatic control system. So this is the diagram for automatic control system. This is the reference input, error detector, controller, open loop system are also called plant, and output. The output is feedback to the input. Examples for closed loop system are automatic control system, air conditioner, water level controller, missile launching and auto tracking by radar, servo voltage stabilizers, automatic electric iron, cooling system, etc. The components of automatic systems. The basic components and automatic systems are error detector, amplifiers, controller, actuators, plant and feedback. So we can see this is the block diagram of automatic controller. Reference input. Reference input will be an input signal proportional to the desired output. Error detector compares the reference input and feedback signal If there is any difference, it produces an error signal. Actuators amplifies the control output and converts to the required form of energy that is acceptable for the plant. Feedback system samples the output to produce a feedback signal which is proportional to current output. This diagram shows how a closed loop feedback system works using everyday example of driving a car and controlling its speed. So this is the desired output. This is the controller and actuator. Plant is called your car and speed as the output, and sensors, your eye act as a sensor which will be as a feedback connected to the input. The difference between open loop system and closed loop system: mainly in open loop system is also called as non-feedback system. Closed loop system can be called as feedback system. Open loop system is very simple in construction, whereas closed loop system is complex in construction. Open loop system is non-reliable, whereas closed loop system is reliable. Open loop system is a stable, closed loop system is less stable as compared with open loop system. Open loop system is a faster, whereas closed loop system is slow. Open loop system is a non-linear, here closed loop system is a linear system. Next, mathematical models of control system. Why we need mathematical model? The mathematical model is used to study and predict the behavior of the control system with help of differential equations. The response or output of the system can be studied by solving differential equations for various input conditions. The mathematical model of a system is linear if it obeys the superposition principle. The principle of superposition can be expressed diagrammatically as shown in the figure. Let H be a linear system. X1 of t is the input signal and corresponding output is y1 of t. There is another input signal is called x2 of t. The corresponding output for the system, second system, is y2 of t. So these two input signals are multiplied with the constant a1 and a2, which are added to the adder and which can be written as a1 x1 of t plus a2 x2 of t, which is the input to the system. The output will be y3 of t, which means y3 of t equals a1 y1 of t plus a2 y2 of t, which is equals to a1 x1 of t plus a2 x2 of t. Types of systems. Mainly there are three types of systems. One is mechanical system. Under that, mechanical translational system, mechanical rotational system. Second one is electrical system. Third one is electromechanical system, which means combination of electrical and mechanical. First, mechanical translation system. So the model of mechanical translation system can be obtained by three basic elements. First one is mass, which is called weight of the system. Second one is spring, called elastic deformation of the body. Third one is dash part. This is friction existing in mechanical system. The list of symbols used in mechanical translational systems. X represents displacement in meters. V represents velocity, which can be written as dx by dt. A represents acceleration, which can be written as dv over dt is equals dt d square of x over dt square, where F is called applied force, Fm is called opposing force offered by the mass of the body, Fk opposing force offered by elastic of the body called spring, Fb opposing force offered by the friction of the body called dash part. As I told you, m is the mass in kg, k is the stiffness of the spring, b is the viscous friction coefficient. Next, force balance equations of idealized elements in mechanical translational systems. So this is the ideal mass element. So one end is fixed here. F is the applied force. Fm is the opposing force due to the mass. X is the displacement. So Fm is directly proportional to d square x over dt square, or also we can write as Fm equals mass times d square x over dt square. Next, dashpot. One end is fixed here, so it is called ideal dashpot with one end fixed to reference. So here again F is the applied force, Fb is the opposing force due to friction, x is the displacement. So Fb is directly proportional to velocity, which is equals to Fb is equal to b times dx over dt. So by using the Newton's second law, we can write applied force is equals opposing force, which is equals to b over dx over dt. Next, ideal dashpot with displacement at both ends. So here before and after. So before the displacement we are calling it as x1, after we are calling the displacement as x2. Fp is the opposing force due to the friction or dashpot. So Fb is directly proportional to, we can write like a d over dt of x1 minus x2, because here the dashpot with displacement at both ends. So we should write like this. So B of P is equal, the equation will be written as B times d over dt of x1 minus x2. So based upon the Newton's second law, we can write this equation as F, which is a applied force, is equal opposing force Fb is equal to b times d over dt of x1 minus x2. Next element, ideal spring with one end fixed to the reference. Again here F is the applied force, X is the displacement, Fk is the opposing force due to elasticity. So here Fk is directly proportional to X. So we can write Fk is equal to K times X. K is called spring constant. So based upon the Newton's second law, applied force F is equal to opposing force Fk, which is equals to K times X. Here ideal spring with displacement at both ends. So both ends there will be displacement. Before the spring there is a displacement is called x1. After the element where the displacement is called x2. So Fk is proportional to x1 minus x2. We can write as Fk equal to K times x1 minus x2. So based upon the Newton's second law, F is equal to Fk, which is equals to K times x1 minus x2. Next, Laplace transformation. First, why we need Laplace transforms in mathematical modeling. So in control system, the mathematical model is usually represented by differential equations. Solving these equations directly in time domain is quite difficult. Therefore, we use the Laplace transform to simplify the analysis of control systems. So it converts time domain into S domain. So what is Laplace transformation? The ratio of Laplace transform of output signal to the Laplace transform of input signal at a zero initial condition. So we can write Z of S represents the Laplace transform Z of S equals, like this symbol represents the Laplace transform L of output over L of input at zero initial condition, which can be written as Z of S is equal to output of S over input of S. Next, mechanical rotational system. In this, the mathematical model of rotational system can be obtained by using three basic elements. One is moment of inertia called as J. Second one is a dashpot with rotational frictional coefficient B. Third one is torsional spring with stiffness K. So the list of symbols used in mechanical rotational systems. Theta is equal to angular displacement in radians. D theta over dt we can call it as angular velocity. D square theta over dt square angular acceleration. T applied torque. J moment of inertia. B rotational frictional coefficient. K stiffness of the spring. Torque balancing equations of idealized elements in mechanical rotational systems. So the first one is ideal rotational mass. So here T is the input torque, theta is the angular moment. So T is a directly proportional to d square theta over dt square, which can be written as Tj equals j d square theta over dt square. So based upon the Newton's second law, T is equal to Tj is equal to J d square theta over dt square. Second element, ideal rotational dashpot with one end fixed to reference. Here T is the applied torque, theta is the rotational moment, and B is the dashpot element. So the TB is directly proportional to angular velocity, which can be written as TB is equal to B times d theta over dt. Based upon the Newton's second law, we can write as applied torque is equal to opposing torque is equal to B d theta over dt. Next element, ideal dashpot with angular displacement at both ends. Here one end is fixed. Here both ends So now based on this, we can write the torque equation as TB directly proportional to d over dt of theta 1 minus theta 2, which can be written as TB is equal to B d by dt of theta 1 minus theta 2. So based upon the Newton's second law, T is equal to TB is equal to beta times d by dt of theta 1 minus theta 2.